Work is related to the change in potential energy. Work is the negative of the change in potential energy, or the change in potential energy is equal to the negative of the work. And the change in potential energy, as I illustrated in the previous example, is Q multiplied by the potential, the electric potential difference, or the voltage difference. So you have, in this case, the voltage difference when the charge moves between A and B, it is VB minus VA. One important observation here: no network is required to move a charge between 2 points that are at the same electric potential. If they are at the same electric potential, then you are talking about equipotential surface. So VB is equal to VA, and the difference here is 0. So there will be no change in potential energy. If there is no change in potential energy, then there will be no work needed. Okay, so you can move charges freely on an equipotential surface without the need to do any work, because the change in potential energy is 0. Okay. Now, if you have a conductor and you have charges on that conductor, at equilibrium, the surface of the conductor will serve as an equipotential surface. If the potential was not equal at all points, then there will be a potential difference. If there is a potential difference, there will be a field associated with that potential difference, and the field will do work, and that work will redistribute the charges. So charges will start moving. But if you are talking about electrostatic equilibrium, then at electrostatic equilibrium, there is no potential difference. All points will have the same potential at the surface of the conductor, and the electric field lines will all be perpendicular to the surface, as we illustrated last lecture. This is usually what we have for conductors. So the electric potential is a constant quantity. It is constant everywhere on the surface of the charged conductor, and we are talking here about equilibrium. This is the case in equilibrium. If they were not equal, then charges will redistribute themselves until they reach equilibrium. Also, the electric potential is constant inside the conductor, and in fact, it is the same value as the electric potential at the surface. So the inside and the surface, when it comes to electric potential, have the same value. One other quantity of energy that we use is the electron volt. 1 electron volt means a charge of 1.6 by 10 to the minus 19, which is the charge of 1 electron, being accelerated through a potential difference of 1 volt. This unit is important in atomic physics and in nuclear physics. It's a small amount of energy, but this is the kind of energy that we deal with in atomic and in nuclear physics for electrons and for protons. So this is the conversion formula. 1 electron volt is 1.6 by 10 to the minus 19 joule. An electron initially at rest accelerates through a potential difference of 1 volt, gaining kinetic energy, whereas a proton also initially at rest accelerates through a potential difference of minus 1 volt, gaining kinetic energy. So here, because the charge is different between the electron and the proton, electron is negative, proton is positive, so you need to flip the sign here. Of the following relationships holds. As long as the charge is the same, it is E for both electrons and the protons, and the potential difference is the same, it is 1 volt. So the kinetic energy change will be the same for the electron and for the proton. In general, when we talk about equipotential surfaces, if you have a point charge like this, when you calculate the potential KQ over R, all points on this surface will have the same potential because they share the same value for R. If you move to another value of R, you will have another equipotential surface. If you move to a third value of R, KQ over R, again, you have another equipotential surface, and so on and so forth. So for a point charge, equipotential surfaces will be spheres, spherical like this, and the electric field lines will be radial like this. You can see that always the electric field lines are perpendicular to the equipotential surface. Another observation, the electric potential, which is KQ over R, as R is smaller, the potential will be greater. As R gets greater, the potential will decrease. As R gets greater, the potential will decrease. The potential will continue decreasing. So from here, you can deduce that the direction of the electric field goes with the same direction of decrease of the electric potential as we move on these equipotential surfaces. Okay? The direction of the electric field is the same as the direction of decrease for the electric potential. If you have a dipole here, you have negative charge and positive charge, then these are the electric field lines as we explained last lecture. The equipotentials will be surfaces that are perpendicular to the electric field lines. So these blue curves are the perpendicular curves on the electric field lines. Therefore, they represent the equipotential surfaces for the dipole. Okay? So this is how we define the potential for any surface defined by a radius R. One nice application of what we learned is the electrostatic precipitator. Here, a simple design where we use the high voltage. We have in this design this setup with this wire connected to high voltage something like 40,000 volt. And the idea here is to reduce the pollution to the environment. This is without the precipitator, it's not operating. This is when the precipitator is operating. So here, the dirty air comes in, and because of ionization, the device removes the particulate matter from the combustion gases, and this reduces the pollution. So here, the dirt is accumulated and it can be taken out rather than polluting the atmosphere. Another application of electrostatic is the photocopying machine, lithography, that was invented in 1940. Also, laser printers follow a similar procedure. So here we start with a photoconductive surface that is given a positive electrostatic charge in the dark. Then the page to be copied is projected on the charged surface. Here we have an optical system with this lens that will project the page to create an image for the document. Then the negatively charged powder, which we call a tuner, is dusted into the photoconducting surface, and the charged powder adheres only to the areas that contain the positively charged image, which has some details of the image. So this way it is transformed to the positively charged paper. Finally, the tuner is fixed by heat, and the result is a permanent copy of the original.